Thank you very much, Alessandro, dear colleagues in Central Asia. So I will try to give you an introduction to the RAMS model, and more generally, not just the RAMS, but the numerical modeling of mud flow, debris flow, GLOFCs in the context of risk management and hazard management. So I won't talk much about RAMS, but more why are we doing this course, why it is important to have capacities and capabilities of numerically modeling such flows. So I will share my screen. Just a second. Probably. Do you now see the presenter? So the normal view, is that okay?
We see the presentation, yes, Christian, it's good.
Okay, perfect. So welcome to this presentation. What you see here is obviously a glacier lake, and on the left and the right, on the left-hand side, you see a typical result of a RAMS model. Here indicated the debris flow with different flow rates. On the right side, then you see a hazard map, so the product of numerical flow modeling and fieldwork. Now, we start in about glacial lakes, and you know glacial lakes are very dynamic. On the right-hand side, you see the example of Bogatyr Lake in Kazakhstan, as published recently in a very interesting paper. And this is very interesting because it shows how the lake developed over the past 50 years in response to glacier change and retreat. In Switzerland, of course, we also are faced with problems and risks of glacial lakes. On the left-hand side, you see the evolution of a quite famous glacier and glacial lake in central Swiss Alps, how this impressively developed from a lot of ice to a lake. And now discussions are about, this is just a simulation, but discussions are about using this lake for a hydropower dam. So there's also potential benefit of glacial lakes. Discussion that is ongoing, but you know that glacial lakes are also an important hazard and risk to life. What you see here, this is one of the biggest GLOF disasters in history in Peru, where in 1941, a GLOF destroyed much of the city of Huaraz in the Andes, at 8,000 meters above sea level. On the lower image, you see the city today, and approximately the lake is still there, actually has grown impressively, and approximately what part of the city would be affected potentially by a GLOF. Now, how do we position the GLOF modeling? Here it's good to have in mind the risk concept, and we refer here to the risk concept of the IPCC, where risk is a function of hazard, vulnerability, and exposure. If we look at this graph, this is a bit more detailed, a bit more visual. You see the hazard. I take just a second. I take a laser pointer. So you see, this is the origin of the lake. Then you have this flood, and you have the exposed community. So we have exposure and also the vulnerability, so how vulnerable they are to such events, how well or how badly they are prepared. Maybe you know the integrative risk management, which starts with an event disaster. Then you have response functions. Then it starts to recover, the recovery, and then everything which is preparedness and prevention, with the aim of reducing the risk. I have for you here this graphic, which is just developed in Switzerland, but other countries have similar concepts. In some more detail, once event hits, then you have in immediate response, you know, the countries' immediate response actions. Here, then also constructions start to recover. For instance, here to extract all the sediment deposited to increase the retention function. Then we go into event analysis, reconstruction, and then we come to prevention. And here, for prevention, hazard maps, which are nowadays often based on numerical modeling, they take a very important role because they are also the basis for land use planning and for many other things, which I will show you in a few minutes. And of course, monitoring is also very important, and monitoring is also part of early warning. Now, very specifically about what is the purpose of GLOF modeling? What can we do once we are fit to use the model RAMS? Why are we doing that? One block is really important. The modeling allows us to better understand the GLOF processes. On the other hand, what's also important is to use the model, it's important to have some basic understanding of GLOF processes, because then we can apply the model much better. I have sketched here a number of functions that are important. So GLOF modeling, I've already mentioned, is very important for hazard mapping, which then is also important for drawing, for instance, hazard map and evacuation maps. Also, evacuation times can be extracted from GLOF models. Early warning, of course. In the GLOFCA project, we have a main focus on early warning systems, early warning. So we need these modeling studies. And this goes to information to authorities and the public. And then we have the very connected, the risk analysis that of course also feeds into early warning. That's very clear. Risk analysis also goes to spatial planning, and then to planning of structural measures on the one hand, for instance, dams, and on the other hand, also to information to authorities and public. This one here is also taken from the recent publication, Medeu et al., which also shows nicely in a little bit, maybe a bit more technical details on how you assess lakes, dangerous lakes from remote sensing. So this is satellite image based. Then you have field investigations, and basically here we have the modeling part. So modeling of peak discharge and downstream effect, which then allows us to identify the hazard of the lake. Now, quite important, this slide here, and I think this is also a question you pose to yourself. There are several models, and which models should I actually now choose? Which one is the best for me or the best for our institutions? That's an important question. I list here a number of models. This is not a complete list, of course. Some of these models are commercial. Other models are more experimental, are more in research, and some of those are a bit between. First, we have here RAMS, and I tell you also a few words why we decided, or why we think RAMS is a good model for the purpose of in Central Asia. These are all dynamic, I would call them dynamic and physically based flow models. We have Flow 2D, which started off many years ago, is still a commercial, an important commercial model, quite widely used for flow, for inundations, river flows, and also debris flows. Titan 2D, which originally developed for volcanoes, but has also been used beyond that. Dan 3D is certainly an important model for landslides and debris flows, widely used. Then Flow 3D is also under this widely known. Or an important one, an interesting one is also our AvaFlow. This is a more recent model. It's implemented in GIS environment. And finally, Basement. It's a model which was developed by colleagues at ETH here in Zurich. For instance, I show you a couple of examples to, for instance, model dam breaches. Then I list here also what I call hydrotopographic flow models. Many of those work in a GIS environment. The GLOFCA, this is coming from volcano research, looking at lava flows and lahars. Or we have the quite famous, well-known lahar set model that has been used extensively for volcanic debris flows. Then there's another models we use still quite a lot, MSF, modified signal flow, and yet another one. So you see this is a list, and I tell you it's not complete. The very important point is no model is perfect. All the models have their pros and cons. So they have advantages and they have disadvantages. The point is really to select the appropriate model for the respective application and project. And here, for instance, criteria could be input data, output, what you want, the time you need, the cost and resources, etc. Why we have chosen RAMS, or why we think this is a good choice for you. RAMS has been developed over many years by our colleagues from the Snow and Avalanche Institute in Davos, part of WSL. And it has reached a high degree of robustness. So it's really robust in using. It's also relatively straightforward, relatively simple to use. And some of these models listed here are rather complicated to use and are less stable. So it's numerically also stable. It requires input data, but not a huge amount of input data, which sometimes the number of parameters, there are a number of parameters which you will learn, but it's not an infinite number of parameters, and you can just manage it. On the other hand, the output is very important and interesting. For instance, flow height is very important for hazard maps. Flow velocity are one of the key output results we will use later for instance, producing hazard maps. RAMS is also widely used and tested and verified in many regions of the world, and we have very good collaboration with our colleagues from Davos. But also to say, if you now learn this model, several of these models have the basic principles are similar, so you will also have an advantage if at one stage you want to learn or use another model. Now I want to show you a few things, what can be done with numerical models, not only with RAMs. I also show application with RAMs, but also with other models. For instance, here a case in Argentina, in Mount Tronador, a glacial lake that developed over the past decades and produced quite an important GLOF in 2009. This is now an application with the model basement. And what you can see, this is actually, there was damage here, but it was not, fortunately not a big disaster. So for us, it was also very important to learn to understand the process. And with the model, for instance, we were able to reconstruct a discharge. And this is a moraine dam failure. So it's really this breach widening process with erosions at the moraine. And for instance, what I think is interesting, sometimes people think a moraine breach happens within a few seconds or minutes, but this is not the case. You can see this happens over something like 2 hours. Of course, it can go faster or slower, and it can reach here, for instance, 4,000 cubic meters per second. So very high discharges. And if you have a larger lake, topographic conditions could also even be larger. Then here, also very interesting, you see how the breach width develops, the breach depth, and how the lake level drops, and the flow depth. So these are all important parameters to know. And then flow velocity over time and the shear stress. The shear stress, you see, increases. There's really the stress also on the sediment. Erosion increases until the point of maximum discharge and then decreases. Many GLOF processes include cascades of, for instance, a classical cascade is that you have a landslide, a rockfall, an avalanche that falls into the lake and then produces an outburst flow over the dam. This is indicated here. We have, in some applications in Peru, for instance, we have looked at such a cascade and how you can couple. We have the initial avalanche here. This is a nice avalanche. We have run many model runs with RAMs and produced basically the height, the flow height of the avalanche and the velocity over the impact time. And then this was the discharge. We have calculated the discharge at this point here when the lake was hit. And then with another model, this is another model that is a hydrographic model, the eBear model. We simulated here the dam overtopping. And you see here, these very high discharges with the dam overtopping. And then again, I will show later, we used RAMs to model the GLOF. So in this case, we coupled different models. Or here an example, this is also from the previous case. You see here, for instance, we looked systematically at different avalanche volumes from 400,000 to 1 million. And you see that the larger the avalanche is, the higher the overtopping heights, here the red dots, and also the maximum discharge, which can go to several 10,000 cubic meter per second. I also would like to direct you here to the GAPAS international guidelines. GAPAS is an international commission on glacier and permafrost hazard in mountains. And for those who have not yet been able to be informed about this, you are very welcome to join this as a member, this international commission, and contribute and benefit from the expertise. Please go to gapas.org. In this guideline, which we presented back in November in Tashkent, I just want to remind you that we have this susceptibility and stability assessment. So we look at the situation of the lake and at the surroundings, and then we define the hazard modeling. So we work with 3 different scenarios in this case, and this is actually here. Here we look the physical numerical modeling. This is where RAMS is coming into play. And I show you this also here. This is a bit more, maybe a bit more complicated, but just to show you. So we have the avalanche, then this goes the impact wave, the outburst flow height. We calculate the intensities, total flow heights, and then we produce different hazard levels, which eventually go into a hazard map. This is like a flow chart and procedure that can be followed for producing hazard maps. For the hazard maps, for instance, there can be 3 different hazard levels from low, medium, and high. And this is often a function of the probability of occurrence of a scenario and the intensity. So very high flow heights would be classified as high intensity and highest danger level. In Switzerland, we have guidelines, official guidelines in terms of what levels are needed. For instance, for debris flows, if you want for medium intensity, this is a level of 1 meter. High intensity, more than 1 meter. For rockfall in Switzerland, we use energy. An example of this from South Lunak in Sikkim, India, Himalayan state, where we're also working on with colleagues in India, and based on RAMS, for instance, you produce flow depth and flow velocity, which is then converted to an intensity map and eventually to a hazard map. Or this one here, again, this is the same case I presented early in Peru, where we typically model 3 scenarios, and for definition of the scenarios, we need to do this stability and susceptibility assessment, and of course field work. And you see these 3 different scenarios, how they evolve, and this is the city here and what is affected. Now what's very important, and that's also then the next slide, you can calculate here in the colors, you have the different flow levels. But you can also produce these hydrographs, and these are really important, a bit small, I know, but this tells you how long the GLOF takes to a certain point. And for instance, it gives you here, the GLOF takes 65 minutes to reach the city in the medium scenario, or if you have a large GLOF, which is obviously faster, then it takes only 35 minutes to be there. So this is really a key asset of a model like RAMS, then also for early warning, because you need to know when a GLOF would arrive at a certain place, community, or infrastructure. So early warning numerical modeling is very important for early warning design and implementation of an early warning system. This is an example. For instance, you have here stations, meteorological stations, camera, sensors, pressure sensors in the lake, etc. The data is transmitted then to the city. And hazard and risk analysis and mapping is one of the important components for early warning system. For instance, here this is the center, the data and communication center in the town. And obviously it's very important that this is located in a safe place, green here. We have seen cases where such operational centers are located in high hazard zone, which is of course not a good thing. Or then for the ones you produced from here, you see here a hazard map, and from the hazard map can be a very good basis for an evacuation map. Here you see this evacuation map, and you see the arrows indicate the direction of evacuation in case of event. And then, of course, in the field, you have all indications that indicates where you have to go in case of evacuation. And of course, you know that very well, this also includes important training, information, provision, etc. with local population, and in this case, in schools. With modeling, we can also look into the future. And not just a little bit ahead, but also in 10 years, 20 years, 50 years, etc. If we want to model, for instance, the effect of glacier retreat on lake development and future GLOF hazards. This is an example in Peru. This is not TREMS. This is a GIS-based model. That's somewhat simpler. It models past GLOF on the left side. On the right side, you see potential future GLOFs depending on the warming scenarios, different warming scenarios which are indicated here with the RCPs, which are the representative concentration pathways. 2.6 is low-level warming in the future, and 8.5 is high-level warming. And then we calculated what are the effects of these warming scenarios, glacier lake formation for the future for this region, or for larger regions. For instance, here in the Himalaya region, we have a current and future GLOF risk, also depending on different warming scenarios. So from low present to even ice-free, and this was also calculated with a computationally fast and simpler GLOF model. But just to show you what you can do with GLOF modeling on this level. Now, I would like to put this in the larger context for you from overall risk management options. GLOF modeling is highly relevant for virtually all risk management options, and I already have touched on several of them. Let me some examples, for instance, lowering of lake level, siphoning, or increasing the channel. Your colleagues in Central Asia have quite a bit of experience in that, and in former times, of course, this was possible without modeling. But with modeling, I think you can do it even much more targeted, because you can, with the GLOF model, you can see, okay, which is actually the lake level, how much do I need to lower the lake so that we can have safe conditions, and how can we calculate safe condition? This is where we use GLOF numerical modeling. Or artificial drainage channels, reinforcement and enhancement of river cross sections. This is also from the GLOF model. We can, for instance, find out where are the critical conditions or critical locations along the downstream flow, and where do we need to make such measures like protection from erosion. Of course, the field experience and the field work is also still very important, but the modeling gives us additional information. Then the evacuation, the reduction of exposure. I have talked about this, that we need evacuation maps. Evacuation maps are best informed by hazard maps and risk maps. So that's very important. And then this is maybe even the most important area of application of GLOF modeling for spatial planning according to hazard maps. So GLOF modeling coupled together with fieldwork is very good for producing hazard maps. And also, finally, for reduction of vulnerability, with GLOF modeling, we can produce hazard maps which serve as an important information to authorities and population. For early warning system, just once, because our GLOFCA project, this is the main focus. So modeling goes very much into risk knowledge. But as I mentioned also in the monitoring, response and communication, as a basis, we need this type of modeling. And before I come to conclusion, I just would like to mention again here the guidelines and the network of experts of gap paths, which in case you should not yet have the documentation and the guidelines, which are also available in Spanish, please go here to the website and please join also this commission as a member. My conclusions and recommendations. Over the past years, numerical modeling of mass flows, and this includes landslides, debris flows, mud flows, avalanches, and GLOFs, have become an indispensable tool for hazard analysis, mapping, and risk management. This is really over the past years, this has evolved very strongly. We have seen there are several models available, and they are useful depending on the process to be modeled. So mud flow, avalanche, not all the models are work for all different processes, of course. And then the scale, do you want to do it very locally or regionally? That's also important because some models are very detailed, but they are computationally slow, so they can only be used at local levels. Some others are faster and can also be used at the larger spatial scales. The level of detail you want to produce, the input data required, how much input data do you have, what is the resolution, for instance, of your digital elevation model, etc. Then financial costs. Some of the commercial models come with a license cost, of course, then support and maintenance. Is it an easy model to handle in your institution, or is it a complicated model? I mentioned that the basic physical principles are often relatively similar. Very important, I mentioned it throughout. Mass flow modeling cannot replace fieldwork, which is very much required for the input data verification and adjustment of results. And this brings me to this point. It's really important that you are critical with the model. The model produces a result, and it can actually produce any result. But the model produces usually the kind of result, or the result is as good as the person that runs the model. So sometimes people tend to be to overestimate or overtrust the model. So be always critical with the result of the model, even if it looks very nice. And finally, I also mentioned this, it's of course, using the models, it is very important that you have a reasonable understanding of the physical processes. You can, of course, run the model without much understanding of the physical processes, but the model result will be much better if you have a reasonable understanding. And this, of course, very much from all your big experiences in these mud flow and GLOF processes. So here I am at the end of the presentation. I thank you very much for your attention, and I wish you a very successful course today, and then next webinar, and of course also then the on-site course in Almaty later in June. Thank you very much.